Dr. Vrudhula is a professor in the School of Computing, Augmented, and Augmenting
School of, even I forget.
and
School
Augmented
of,
Intelligence.
School of Computing and Augmented Intelligence,
Right.
as
So
opposed to artificial.
So he has his PhD in electrical and computer engineering from University of Southern California, and master's also in electrical engineering from there, and a bachelor's in math in University of Waterloo, Ontario, Canada. And he's a fellow of the IEEE since 2016. Dr. Vrudhula is very well known in the area in the chips domain, and he was when I was a student at ASU as a PhD student, he was one of my professors. So I'm excited to have him here, and I'll let you.
Thank you very much. Good morning, everyone. Thanks for coming on a Monday morning. I think Mondays and Fridays are not very good days for attendance, I know. And I'd like to thank Jayant for, I have this already.
Okay.
Yeah. So he's been showing me around all through the weekend. One day I hope to return that hospitality. I'm not sure if I can. It's been a great visit already. And also I'd like to thank Rihanna. I don't know if she's here. There she is. Thank you very much for doing all the setup for my visit. I greatly appreciate it. So let me get started on this. So one of the things, the title of this talk, Co-Design of Devices, Circuits, and Architectures for Energy Efficient, and I put AI and ML in parentheses for a particular reason, energy efficient computing. And before I get started, I want to sort of tell you who did the work. Professors don't do much of the work. Most of the work is done by graduate students. And I think, why is this not? Okay, so this is, oh, there you go. Is it working? Yeah. Okay. So, so these are some of the students who contributed to the work. The top 3 are still with me. The others have graduated and left. So I greatly acknowledge their contributions to what I'm about to present. The other is several sources of government and industry funding in the past as well as ongoing. Several grants, actually quite a few grants from NSF that funded this work. Arizona, the state of Arizona through their Science Foundation Arizona. We used to have an UCRC Industry University Cooperative Research Center called the Center for Embedded Systems. And now we have a program called IDEAS. My own contribution to that IDEAS was the name. Everybody else's, the real work is being done by others. So it stands for Intelligent Distributed Embedded Applications and Systems. So to get started, before I delve into details, I'd like to take a few minutes to sort of provide some sort of context to this work, okay? And in this, so the title says Co-Design of Devices, Circuits, and Architectures. And the question is, we've been doing this for 50 years, right? So you would think, well, haven't we gone past this already? Isn't this all the VLSI design, chip design? What's there left to do, okay? And I asked this question because this is really the question I asked myself when I was trying to figure out what to do next after AI and ML took over the world, okay? So here, if you look at what's been happening, what happened in the last 2 decades, CMOS technology has been the dominant design technology for now more than 50 years. And we've shrunk devices down to unimaginable sizes. So this is a really nice picture of sort of a graphical display of Moore's law. And if you look at the 1981 to 2002, you get a sense of what the dimensions of these devices, circuits are. Now, from 2002 to now is exactly the same level of scaling that has taken place. So you can imagine the level of miniaturization that has taken place, okay? So now as we've been going down to this descent towards zero, if you will, year after year after year, we've been hearing about how Moore's law is going to come to an end. But year after year after year, there are enormous number of circuit innovations that have been taking place and it's still alive, right? So here, if you look at the technologies that we have, planar CMOS that you see on the you see this? Okay, right there, can't see it. So the planar technology has taken us for, until the year, for almost 40 years, it has been dominant. Then around 2010, it was the first 3D transistors. FinFET technologies took us to amazing levels of miniaturization and compaction. And now even that is coming to a retirement age, right? So what's on the horizon? Ribbon FETs. These are three-dimensional transistors. And even stacked CMOS transistors. Higher, again, both of these are 3D devices. And these are expected to give another 50% reduction in in scaling, right? Independent of the actual technology. So regardless of all of this, from a circuit design point of view, what you and I might be doing, if you're not in material science or if you're not in IC fabrication, how does it impact us in any way? Well, ultimately, whether it's ribbon FET or stacked CMOS or FinFET, we're going to get design sort of abstractions, and ultimately we will be designing with logic gates, NAND gates, NOR gates, and so on. Okay, so the design will continue with logic gates. So what happens in this? Is there anything left to do? So let's take a look at first what the nature of the design. The first thing is, today, how do we design circuits? Well, we start with some abstract specification, not so abstract, but an RTL level specification of a design. And then we go through this synthesis process, where we convert that to a netlist of logic gates. And this is, when we say we, I'm talking about this is fully automated, right? So what we do is we write that specification, and almost the rest of it is almost entirely push button. Then we bring in a cell library into this, and this is provided by the foundry. And then it goes through another optimization phase where we map subgraphs of my logic graph onto a network of cells. Once you have a network of cells, you can do a physical place and route, algorithms again, automated place and route, and then you provide a layout that you can send to the foundry for fabrication. This is now completely automated. Okay? So to some extent, the only thing that's left for us to do is that first part, which is the RTL design. And the other part of this is that this flow cannot be disrupted. So anything you and I invent, and if we want this to see the light of day and have an impact in the real world, we're straitjacketed into following this particular path. The only thing we can do is provide that and maybe modify the cells that we have here, but this synthesis, this entire flow is completely fixed. Okay. The next one in my title is this AI ML computing. Okay, let's talk about that for a moment. I put this in parentheses because the techniques that I'm going to describe is actually applicable to a much broader class of algorithms. In fact, they're generally applicable to data-intensive or memory-intensive computations. AI ML just provides just one particular domain of this data-intensive and memory-intensive computing. Okay? The focus here is not on AI and ML, but on the underlying computations. Okay? So what has happened in this domain? We've replaced algorithms, and I think most of you might be familiar with this. We've replaced algorithms with what we call parametric models. Okay? And these parametric models essentially relate large input spaces to large output spaces. And these models relate these two spaces through a collection of parameters. Data that input-output data, so-called training data, is used to estimate those parameters. And that estimation process is referred to as training. Okay? Now, and this training is, once you train, that is, once you compute those, the weights or estimate the weights, you compute the models, you evaluate those function graphs, and that process is known as inference. Okay? So how do we represent these graphs? Well, we represent these graphs as what we refer to as neurons. These are nothing but inner product computations over some domain. So you have a linear weighted sum of the inputs with some bias, and that's the input-output relation. W is unknown, and if you give me the inputs and outputs, I can estimate the W's and then execute this. So this is one neuron, what we refer to as one neuron. This is a layer of neurons. So you just stack them in parallel. You get a layer of neurons. Now that model is simply, instead of input vectors, you have input matrices. Okay? And then you can take these single layer neurons and connect some large number of layers of neurons, and you get a network like this. And these could be in the thousands. These dimensions of these matrices can be enormous size matrices. This is really the nature of the computation, underlying computation involved in this AI and ML computations, right? Okay. The basic component here is the inner product processor, which is essentially the weighted sum of inputs and weights. Okay? And for historical reasons, it's referred to as a neuron. I'm still not sure why they do it, but it's fine. So we're computing these types of graphs, function graphs, where the underlying operation is function composition. That's all it is, just function composition. Okay, so here's the neural network zoo, as they refer to. So these are the wide range of different types of neural network topologies that people have invented, and there are many more, by the way. And now where we're headed toward is taking these as subroutines. In other words, these graphs themselves become individual nodes in larger graphs. Okay? And so now you can see how the complexity of these networks continues to increase. But there's a large number of these. But essentially, each of these nodes is performing some form of inner product, which requires us to do matrix multiplication and addition, ultimately. That's it. That's the bottom line. Because I'm getting here only to sort of figure out what type of circuitry we need to be able to implement these directly in silicon. Okay. So with that, yes. Yeah. All right. The next part of the title is so-called energy efficiency. Okay? Let's talk about that briefly for a moment, why we need this. If you look at AI/ML's massive thirst for energy, we've seen this, I think, in the last few years. There's lots of newspaper reports about data centers gobbling up enormous amounts of energy, right? So if you look at what it takes to train one of these models, some of these large, and the first one is pretty old now, ChatGPT-3. This has 175 billion parameters. So the W's in that model that I described, that's what that refers to. The number of those parameters is this 175 billion. And you look at the CO2 equivalent emission for training one of those models. That's about 502 tons of CO2. And you can compare this with something that we might be able to understand better, human life or air travel and so on. So you can see where these companies are spending their money. And if you get a sense of what a 502 tons of CO2, this is 1 ton of CO2, and I'm probably, you can imagine where I would stand, where a human being would fit in there, right? So this is what we're spending. Okay, so the next part is, so this is the computation part. So the memory part, so the other part of computing is memory, and in the memory gap, we'll also see that, as you see, that orange line is a line that shows how the sizes of these models are increasing, right? And the green line shows the trend in the size of the main memory that is being delivered to these companies, to the servers. So there's this huge gap in memory. So why does this gap matter? Well, all that data, that billions and billions of parameters, have to sit somewhere. And where do they sit? They have to sit in a DRAM. External memory. You have to bring that memory, all that data into the local cache of the CPU, and then execute. So the more that you spend time, in fact, most of the time one spends is in data transfer between main memory and the CPU, right? And so that's where memory has become the big bottleneck right now, not the compute anymore. Okay? So in fact, people say, Bill Clinton's statement, following what Bill Clinton once said, it's the memory, stupid. That's the statement people make now about where you need to spend your energy in trying to improve the system. Okay. So what is industry doing in all of this? Well, you would think they would, if they're spending that amount of money and everybody's chasing after the same thing. Everybody wants your business. Everybody wants to sell you all their advertisements and all the recommendation systems. They're all trying to sell you stuff. Okay? And so what is industry doing? Well, they're not going to wait in trying to improve any of this AI, any of these techniques. They're not going to wait until they are hungry for the energy. So look at what they're doing. Microsoft is now using the 3 Mile Island nuclear power plant. They're going to use that now to run their servers. Okay? They're building a server farm near the 3 Mile Island. Oracle is also running their data center on nuclear power plants. Amazon is now also running. So you can see their hunger for energy. Okay? You can also think about this. If they're gobbling up all these energy resources, and we can't build energy resources fast enough, right? So now you and I, to keep the lights on, we may be competing with these industries for energy, right? So there is an urgency for sustainable computing, but I think right now the most important thing is trying to get ahead of the curve, trying to beat the competition. Okay? So this is where we are. So what do we do? So let's take a look at the challenges that we have. Does this? Come on. Okay. Let's take a look at this. Addressing the memory bottleneck. Okay? What can we do here? So let's see, why is this important? Well, in this case, if you look at as I said earlier, you have a processor, a compute engine, whether it's a CPU, a graphics processing unit, or a custom accelerator that's performing these operations. You have that control unit, and you have your DRAM, which is a collection of DRAM chips, that DIMM that you put into your PC, into that slot. Each of these DRAMs consist of a bank of memory arrays, okay? And each of these banks of memory arrays what I'm showing you there is a memory array with sense amplifiers and column decoder. And now we're moving away from these single rank DIMM packages to DRAM chips stacked in 3 dimensions. Okay? So this is your 3D high bandwidth memory or hybrid memory cube. So these are now this is the current technology. So the operation here is the completion time depends both on the hardware latency, how long it takes to complete an operation, and the speed at which you can fetch that data from main memory. So even if 80% is in the cache and only 20% is being fetched, 50% of the total time is spent trying to fetch the data from main memory. But even more importantly, if you look at the last line here, it says the energy consumption of data access is nearly 2 orders, actually more, but 2 orders of magnitude larger than a single floating point operation. So it seems reasonable that you want to be able to you want to put the computation and memory right next to each other. And this is obviously true, not just now, but this has been known since the 1950s. Right? We learned this in computer architecture classes about the so-called von Neumann bottleneck. Okay? But we haven't done it. And the reason we haven't done it is principally because of money. Okay? Money and competition. Let's see what the challenges are. The challenges, the first one is the memory business. There are only 3 companies that build memories. One is Samsung, HK Hynix, and then there's Micron. These are the 3 main DRAM companies, right? And they have the entire world market. There are only 2 companies that allow you to make chips, design chips, which is Synopsys and Cadence. Talk about monopolies, right? So, but what happens why haven't we included integrated computation elements with DRAM? First, it's a highly commoditized business, meaning it's highly cost sensitive. They're pinching pennies. A penny saved here can translate into millions of dollars in profit. So they're highly cost sensitive. These are custom designed chips, so they're highly aggressively minimized for power and maximized for capacity. Right? More memory. You want to put as much memory on a die as possible. Once they do this, then the access protocols, the algorithms to access the data from memory, reading and writing from main memory, and the timing cannot be modified. So if you introduce logic into main memory, you have to stick with the existing memory protocols. So you can't touch that. Okay? So these are all black boxes. So you and I as designers don't have really access into this. The other part is no matter what you do, there's very little capacity reduction can be tolerated. So when you talk about using some of that area in the DRAM chip for logic, maybe 10%, 15% maximum is what they may allow, willing to sacrifice. Okay? So very little capacity reduction can be tolerated, and any changes are very subject to very stringent power budget. Right? So if you add logic, you can't. Their logic must be ultra low power, and that area constraint on that. So the logic that you add has to be very, very small. So what does this mean? Well, if you limit the area size, that limits the complexity of the compute elements you can put in there. So you can't put in processors in there without sacrificing a lot of memory. The limited logic also limits the kind of applications that can be supported, obviously, right? It reduces the degree of parallelism. That is, the logic, the further away the logic is from the memory banks, the fewer the bits you can process at any given time. And it adds, obviously, it adds increased latency the further the logic is from the memory banks. So you want to get that logic as close to the memory bank as possible, right? But you have very limited space. So this is what we have been trying to do, meaning researchers have been trying to do in bringing back this notion of the processing in memory, okay? And that's what I want to talk about for a moment. So here, if you notice, so there are essentially two classes of PIM sort of processing in memory architectures. On the left-hand side, there are proposals to build small analog arrays aimed principally for AI ML applications. So what does that mean? AI ML applications, I said a moment ago, are primarily dealing with matrix operations, linear algebra operations. So they're trying to build these arrays of multiply and accumulate arrays, with an SRAM or within a DRAM, primarily using analog circuitry to do it. Okay? The problem with these analog multiply and accumulate arrays is they're very sensitive, they're very small, they're limited in size because they don't scale with the technology. So I don't think that's going to solve the problem. Okay? So the digital elements, all of these different types of organizations for introducing logic and memory depends on where you introduce it. You can introduce it very close to the array, the memory array. You can introduce it near the bank, or you can introduce it outside the bank. Okay? So we have different types of places where we can introduce these arrays. So here, so imagine now, you have your CPU and your DRAM chip. If you look at the bandwidth between the main memory and the control and the processor, you can at most get 64 bytes of data back and forth between CPU and main memory. Okay? 64 to 128 bytes. That's about the unit of data that you can operate on at any given time, right? And when we're talking about gigabytes of information that you have to process, you can see how much you have to do in terms of transfer of data to and fro. The alternate is to put compute logic right near the array, put logic right near the array, right? Near the array, you have a lot more wires coming out, okay? 8K wires, literally 8K wires through each of these memory banks. So, and you can access those 8K wires and perform logic operations in parallel, right? Concurrently. And that's the idea. The problem with this is if you put that logic there, that logic has to have enormously high compute density. Now, meaning it has to be tiny, and it has to be able to do a lot of functions in a very tiny area. Then it begins to make sense, right? Okay. So before I move on, I've been talking about energy efficiency. So we saw some of the trends in the energy consumption. And so what's our target? Meaningfully, if we're going to make a dent in any of this, it should be anywhere from, at least as much as 100x improvement in 2 orders of magnitude improvement in energy efficiency is what is being called for. In fact, more, if you ask me. Okay? So what is energy efficiency? Energy efficiency is simply the number of operations that can be performed per unit of energy, okay, at any given time. So how do we write this? It's throughput, which is the number of operations per second, divided by the power, so it's throughput per watt, which turns into operations per second and joules per second. So it's the number of operations per unit of energy. So that's the energy efficiency we have to fix, we have to reduce. How do we do that? Well, here's the broad strategy. First is to reduce the power consumption, so that it'll increase the energy. And how do we do that? Well, that's what I'm going to present to you in a moment, because a lot has been done in the last 50 years, right? Mobile computing is made possible simply because of the advances in circuitry to reduce power. So we have to go further than what we've been doing until now, right? The next is we need to eliminate that so-called von Neumann bottleneck by introducing logic into main memory. And what this means is we need to devise very high compute density logic. Right? These are the 2 things that make sort of common sense in solving this problem. The next is to increase the operations per second, so increase the throughput by increasing the degree of parallelism. So what does that mean? Well, if you're going to increase the parallelism, you want to, as I mentioned earlier, you want to put the logic that you're going to introduce very close to the memory array, so you get access to as many bits as possible at any given time, right? So that's the idea. So here is the outline of the talk, rest of the talk. I'm going to introduce this notion of high compute density logic, right? What's different? It's AND gates are AND gates, logic gates are logic gates. How much more can you do, right? You can, a little bit. Then we will take that high compute density new logic forms and construct a processing element called what, for lack of a better term, neuron processing element, NPE. What NPE is, it really is just a fancy ALU. Okay? And that fancy ALU we're going to stick inside the DRAM, right near the memory array. And the CPU that's going to interact with the DRAM is only going to transfer a few bits of information, maybe a few bytes of information as control information. All the computation will take place inside the memory array with this compute logic. Okay. So as I said earlier, what's left to do in logic design? This has been known since 1940s. Most of the theory of logic design has been done. Okay? You've taken it maybe in your first year or second year undergraduate Boolean logic class. And maybe if you get to graduate classes, you've taken courses in VLSI design, right? And what's there left to do? And I showed you a moment ago that it's really a closed box. Once you specify your RTLs, provide your RTL specification, there's little or anything that one can do in terms of actually changing that flow. Okay? So I'm going to quote, I'll show you a quote from, there are 2 quotes here, and this is from IMEC Belgium. IMEC is a major microelectronics and semiconductor research organization in Belgium. And look at the first sentence. It says, when it comes to the semiconductor technology scaling, the low-hanging fruit has long been picked. Simply downsizing the patterns of an integrated circuit no longer leads to commensurable benefits. So you can't just talk about shrinking devices. You can only do that so far. The next one says, this is the important quote. One example of beyond CMOS paradigm is quantum computing. The other is majority gate computing, where the result or output of a computation is determined by the majority sampling of multiple inputs. And the reason I point this out is this showed up on the IMEC webpage recently, and we started on this work about 15 years ago, right? And majority gates are no different, also known as threshold gates, threshold logic, right? And I'll talk to you about that in a minute. So the academic world has been doing this for quite some time, right? So what's the problem? Why hasn't this taken over the world? Why am I not rich is what I keep asking myself, okay? Why am I not rich? A good reason. Professors shouldn't be rich. Okay, so the first thing, so let me talk about threshold logic, right? So you know Boolean functions, logic functions, and if you have an input circuit, an input function, there are 2 raised to 2 raised to n functions of n variables. Threshold functions are a subset of Boolean functions, a very tiny, tiny and vanishingly small subset of Boolean functions, but they're Boolean functions. That's the first thing to remember. The second thing is a threshold function represents a predicate. Okay? So this is a Boolean function, 0 and the output is a 0 and 1, but now notice here that this is a threshold, so an inner product with a comparison. So if the inner weighted sum of the inputs exceeds the threshold, this given threshold, then it's a 1, otherwise it's a 0. So here's so these are integer weights, these are Boolean variables, and there's an integer threshold, and this is a logic function, right? Perfectly, there's nothing fancy about this. But the important thing is that representation, which is we saw this earlier in the beginning when we were talking about neural networks, right? So threshold gates are essentially binary neurons. They're also known as artificial neurons, right? So the question is, how do you build a threshold gate? We've done this, many of them, people have done this for a long time. But notice then that entire function is completely specified. If you specify the weights and you specify the threshold, then you know what that threshold function is, right? So here's an example. So I'll just notationally, a threshold gate is like any other logic gate. It has n inputs. Internally, it has these parameters called weights and the threshold. And the output, and this is a clocked circuit, and I'll get to that in a minute, but the output is simply the value of this predicate. If this predicate is true, the output is a 1. If the predicate is false, the output is a 0, right? So it's a strict Boolean function, logic function, right? So here's an example, a couple of examples. Look at the first example. The first example is a 3-variable function, a or b and c. So that's a feeding an OR gate, and the b and c feeding an AND gate, and the output of that AND gate feeds the OR gate as well as the second input. So it's a 2-level AND/OR circuit, conventional AND/OR circuit. But you can also express that particular Boolean function as a weighted sum of the inputs. The first expression is in logic domain. The second expression is in the integer domain, right? So 2 times a plus 1 times b plus 1 times c greater than or equal to 2. So let's see that. The first function a, the first function is a 1 if a is 1, regardless of what b and c are. Look at the second expression. If a is 1, the left-hand side is at least 2, so that is equal to 1. On the other hand, if a is 0, b and c must both be 1. And in the second expression, in order for the second expression to be true, b and c must both be 1. So these are 2 mathematically equivalent functions. You all agree with that, right? So a or bc, or in arithmetic domain, 2a plus b plus c greater than or equal to 2 are identical functions mathematically. Okay? So this would be my logic gate that implements that Boolean function. Here's a much more complex function, right? And this would require several levels of logic to implement, okay, if you implement it using AND gates, OR gates, and so on, right? On the other hand, you notice that, I mean, this can also be shown that these 2 are equivalent. On the other hand, if you notice, the complexity of this representation doesn't seem to have increased that much compared to what you saw in the Boolean domain, okay? And this is generally true. On the other hand, something as stupid as AB or CD, something as simple as this, right, is not a threshold function. So there's only a small subset of functions that have this unique property that they can be represented as a weighted linear sum and a predicate. Okay, with that, let's take a look at how we might be able to implement this function. So what I'm going to do is, this is something that we invented quite a few years ago, and we've implemented this using all sorts of circuit architectures. But I'm going to describe a particular circuit implementation that is important to understand the remainder of the talk. Okay? So here's the circuit that I want to implement. N weights, N variables, N weights, a threshold T, and the C, which is a clock input. Okay? And what happens here is inputs arrive, and when the inputs arrive, internally this magically a weighted sum is computed, right? And it's compared against the threshold, and when the clock arrives, the output will be either be a 0 or a 1. Okay? So here is now, this is the only part of the circuit I'm going to show you, so don't panic, right? I have to do this. It's sort of an interesting circuit. So this, for those who are familiar with flip-flops, this is nothing but the sense amplifier that senses two inputs, those two inputs that are coming in red, in the red signals. These are differential voltages, and it senses those voltages and sets the output to be either 0 or 1, depending on which one is greater than the other. Okay? That's all we need to know. So here, we're going to introduce a bunch of two networks, the left-hand network and the right-hand network, so LIN and RIN. The inputs come to both of these, and the clock is, this is connected to ground, right? So here, so imagine if the clock is 0, there is no conduction path from the supply voltage to ground. So both of these, both N1 and N2, which are the outputs of this, both are going to be 1. So let's take a look at that. So when the clock is 0, this is going to be pulled high, this is going to be pulled high, and the output is going to be set. It's going to be the flip-flop on the output, the latch on the output will not be disturbed. When the clock goes to 1, in this example, let's assume for a moment that I've designed this circuit in a special way such that I'm comparing the conductances of the left-hand network and the right-hand network. So let's assume I apply a set of inputs for which the function is supposed to be 1, in which case the left-hand network is designed in such a way that the conductance of the left-hand network is much greater than the conductance of the right-hand network. So now I apply my inputs, and then I clock the circuit. The clock goes from 0 to 1, and the left-hand circuit is going to conduct faster because that's how I designed it. And if the left-hand circuit conducts faster, this is both these two outputs will go to 0, but the left one will go to 0 faster, in which case the N1 is going to drop, okay? And while the N1 while the N1 signal goes to 0, it's going to shut off the conducting path on the right-hand side. So this is a standard strong-arm flip-flop design that has been connected to two conducting networks. And in doing that, then this will go back to 1, and the output will become a 1 in this case. Okay? So the comparison is being done by comparing the current through the left-hand network and the right-hand network. And they're designed in such a way that any input for which the function is a 1, the left-hand part of the network will conduct much faster than the right-hand part. And any input for which the output is 0, the right hand will discharge faster than the left hand. That's all we need to know. Okay? This is not easy to implement when you have a large number of inputs. Okay. The trick here is, how do we represent these conductances? Okay. You notice here you have a series of parallel transistors driven by the inputs, series of switches driven by the inputs. But you have these little blue boxes there. And these represent some interesting devices that we're going to try to integrate with CMOS technology. Essentially, these are your memristive elements. They're programmable resistors. Okay? These programmable resistors, I'm going to map the weights in my neural network, ultimately in that neuron, the W's in the neuron, to the values of these conductances. Okay? So the higher the weight, the greater the value of G. The lower the weight, the smaller the value of G. So you can think of the G's in here, the conductances, as representing the weights in my neural network. Okay? So in this case, if I have an input which has, if the weighted sum of the inputs exceeds my threshold and the output is supposed to be a 1, the left-hand side is going to discharge first, right? And then the output will be set to 1. If the weighted sum of the inputs is less than the threshold, then the right-hand side of the network will discharge and the output will be 0, right? The key is the technological hurdle that we face now is in those little blue boxes. These are your so-called memristive elements, the emerging memory elements. that offer programmable resistances, programmable conductances. Okay? That's the biggest challenge. Okay, so let's take a look at some of the designs that we have. So the left-hand side is a large D flip-flop, a single flip-flop, okay? Something that we may be familiar with. And all that D flip-flop does is when the clock arrives, it passes the input to the output. Okay? Just stores the value in the flip-flop and passes the input to the output. This is the design of our threshold gate, which is about the size of a D flip-flop. Okay? Not that much bigger. Okay? And this is, implements a 5-input threshold function, in 5 or fewer input threshold function. And the conductive elements here that were used here were also programmable MOSFETs, not necessarily memristive devices, programmable MOSFETs. So we want to see what kind of, this is a single flop about the size of a D flip-flop. Okay? So what kind of functions can this thing realize? Okay? In this case, if you look at, these are the set of functions that this can realize. So these typically would require 3-4 levels of logic in a conventional CMOS logic circuit, would require 3 to 4 levels of logic, which we can implement in a single cell about the size of a single D flip-flop. That's pretty good. That's a pretty good amount of, this is what I'm talking about when I say compute density, increasing the compute density. Okay? Okay, so the next thing is, remember that we want to have these, the left-hand network and the right-hand network must be widely separated, because the closer they are, that sense amplifier will not be able to distinguish between between a 1 and a 0 fast enough, right? So we want to make those conductances widely separated in voltages. So how do we do that? Well, so we have an algorithm. So I'm not sure how many of you are familiar with standard neural networks, but the standard sort of McCullough-Pitts neuron is a binary neuron that separates the inputs, the 1 inputs from the 0 inputs, right? It identifies the hyperplane that separates it. This circuit is essentially that. So what you have here is the onset and the offset of the onset minterms and offset minterms of a threshold gate are separated by, we want them to be separated by voltages, right? Widely separated voltages. This is what we want to achieve. So here is an example of the design of our threshold gate. So we developed a training algorithm that identifies the G's in the network, right? Identifies how much resistance, what resistance should we apply, should we program the threshold gate in order to separate the zeros and the ones as much as possible. So we have a modified learning algorithm that separates the zeros and ones by programming determining the appropriate conductances in the network. And you notice here, this is your typical CMOS. These are the delays associated with the CMOS gate for all those 117 functions that I showed you a moment ago. And on the left-hand side is the design of a single flip-flop that implements all those functions, right? The delay associated with that single flip-flop. So you have to imagine these the circuitry that is shown, that corresponds to the delays shown on the right-hand side is a fairly large circuit. It has a flip-flop and it has many levels of logic gates. The data shown on the left-hand side is for a single cell about the size of a single flip-flop that has all those functions can be built into it. Okay? So these are at the cell level, these are the kinds of improvements that we get in terms of area improvement, power improvement, delay improvement, and also leakage improvement. That's for a single cell. So how do we use this? Let's go back to our flow, our methodology. We started off with a RTL specification. We generate these logic circuits, and I said we cannot disrupt this flow. So what do? What we do is we take this binary neuron and we design this binary neuron as a standard cell, basic standard cell, conforming to the constraints of the cell library provided by the foundry. Okay? So we were able to do that. So the tools now don't see this as anything else but a typical sequential cell. And they're able to inject this in order to improve the delay or reduce the power consumption automatically. Okay? So we designed these artificial neurons or threshold gates as standard cells, injected them into the library, and let the tool run, do the logic synthesis and design. And in doing that, this is how it would work. So here's a typical logic circuit. The AND gates and OR gates are shown are interspersed with the green boxes are the input flip-flops, and on the right-hand side you see the output flip-flops. So what do? So we identify, the algorithms identify subcircuits that happen to be threshold functions. Meaning, remember, not all functions are threshold, right? But here we search through the network and find subcircuits that satisfy the property of thresholdness, right? That can be represented as a threshold gate. And each of those is going to be replaced with a single flip, our basic cell. If you do that, I showed you there, it's shown as a black box there. That black box is essentially that circuit that I showed you earlier. Okay? The reason I show this as black boxes is because if you remember the G's that represent the conductances in the previous circuit, they're not programmed. They're programmed after you fabricate the circuit. So the function of that cell is not known until it comes back from the foundry. Okay? And that we know how to do because we know what function that's going to implement for that particular instance. This shows you that this particular idea there's an interestingly cool idea about this where you can obfuscate the circuit. So no foundry, when you send your circuit to fabrication, the foundry cannot steal your design. They can't reverse engineer your design, right? It's completely secure, right, from copying as well. So if you do that, now we'll replace that blue one, that yellow one, and that green one, and that orange, the pink one. Those subcircuits will replace with our threshold gates, and the remainder of the circuitry which could not be replaced is also shown there, right? So these black boxes are black boxes because, as I said a moment ago, if you look when the foundry sees this, it doesn't know what the programming of those threshold what the programming of the neurons is. So this remains completely secure from fabrication. Okay, and then at the end, what happens to our circuit? Well, these are injected into the array, into the layout, and this is the result of the placement and routing algorithm, and this is what is sent to the foundry. Okay? And when the foundry comes back, when the chip comes back from the foundry, we program these little black boxes, right, to implement the specific functions that they were supposed to implement. Okay. So we have 15 minutes. I need to hustle. All right. So here, some of the data. What you see here is on the left-hand side, you have a bunch of fairly complex function blocks, multipliers, FIR filters, floating point units, FFT logic, a secure hash algorithm. All of these we implemented using conventional logic and with our threshold and with our modified threshold gates. And you notice here, across the board, you get improvements in area, power, the total interconnect as well. So this is quite interesting because typically when you reduce area, things slow down, right? And because you're using smaller transistors. In this case, we're getting an improvement in area and power consumption, right, without sacrificing delay. Meaning the minimum delay circuit that was designed with the conventional design is the same delay we can achieve using the modified circuit, right? So it's a lower power, smaller area, and equally fast as the fastest circuit you can design. Okay, so this is my compute element, my highly dense compute dense element. And what we're going to do at this point is, since this is so small, we will be able to inject this in the appropriate place in a DRAM array. Okay? So notice here, so these are all the different techniques that have been published recently in the last 5-6 years about using, introducing logic into main memory. The closest is obviously you can go ahead and modify the memory array In other words, you can modify the DRAM cell with analog circuitry to implement simple logic functions. The problem with that, as I mentioned earlier, is that's not a very good idea because no DRAM manufacturer is going to allow you to touch that array. Okay? And there are very limited amount of functionality you can have. So the best place you can inject these is at the near memory array, where you have roughly the number of bits that are coming out of each of those boxes is on the order of kilobits per bank. It's thousands of bits per bank. So you can access thousands of those bits per bank to process a logic operation on thousands of bits. You can perform addition. You can perform all sorts of arithmetic operations in parallel, where the operand sizes, where the number of operands are in the order of thousands. Okay? If you move away from that and go further out, away from the main memory array, then the number of bits available to you reduces dramatically. So here you have 64 bits, and also at the outside you have 64 bits. Is this real? It is actually. Samsung introduced last year, a in-memory processor where they put floating point units in this near bank architecture. Okay? They put 16 floating point units in the near bank architecture, but they had to reduce their memory capacity by 50%. And they showed this as a proof of concept. So it's possible to do it, right? Samsung is the largest memory company, and they're willing to look into this idea of introducing processing in memory. What we propose is to use that in-memory structure where we inject these neurons right after that bit line sense amplifier that we have in the memory array. Okay, so very quickly I'm going to go, how will we do this? We said, well, we'll increase the parallelism by near bank logic, and we'll reduce the power consumption by having this high compute density logic. Okay, so this is where our so-called neural processing elements are going to be injected, right? And how many can we inject? Well, per bank we can inject about 1,024. If these are 8 kilobits, and if you have 4-bit operands, we can inject about 1,024 processing elements per bank in this array, right? So this maximizes maximally utilizes the DRAM bandwidth. And we'll build a neural processing element. You saw that one neuron. We're going to build a neural processing element consisting of only 2 neurons. Just 2 neurons, that's it, right? So 2 flip-flops essentially. And that structure can now implement carry look ahead functions, it can implement comparison functions, and it can implement all bitwise logic operations. The nice thing about this is that when you switch between one function and another, you don't have to reprogram anything. You just have to apply a different set of inputs. You just have to flip the inputs. Okay? So that's something to remember. So here are some of the functions that you can implement. You can implement all sorts of logic functions, exclusive OR functions, carry look ahead, and sum functions in a single cell. And this is what our NPE is going to look like. Okay? I have 10 minutes, so I'm going to rush through this a bit. So if you remember, we had these 5 neurons. I'm going to construct 2 clusters, a primary cluster and a secondary cluster, each consisting of each of these 5 neurons. And then I'm going to build my fancy ALU right here. Okay? My fancy ALU is going to have your standard processor interface, a register file, a read-write selector function. But the yellow part is where we make that modification. So we have 2 clusters, a primary cluster and a secondary cluster, and each of these clusters has only 5 threshold gates. With that, now we can see the difference between this structure and a conventional CMOS equivalent. The area differences is about almost 4 times smaller compared to a CMOS standard cell logic. If you implemented the CMOS logic using threshold logic, you get about almost a 3x improvement in area. So how do these work? Look at the differences in the throughput. So here our NPEs are shown below. This is injected into a DRAM with 1024 NPEs per bank of the circuit. And we're going to compare what a conventional floating point of integer and floating point operations using a conventional multiply and accumulate circuit. Okay? And you see that you get a substantial improvement in both throughput and essentially substantial improvement in throughput. For a 16-bit, you get 3 to 4x improvement in throughput using a 16-bit NPE, and you can go anywhere from 3 to almost 10x improvement. So we're hitting the ballpark of achieving 10x to 100x improvement in throughut. We'll also get that far, energy efficiency, by reducing the power. Okay? So I'm going to skip this part because this shows you, in some sense, this shows you where this technology is going to be implemented in. This is the first 4 stages are the 4 stages of a RISC-V processor. The last stage is the new design that we have for this processing element. There's a memory controller and this new PIM controller. So this is essentially the 5-stage pipeline of a RISC-V processor that we can build this around. And this is now going to go into as part of the input to the DRAM. Now, if you look at the improvements that we get in implementing some of the neural networks, the x-axis here shows some of the commercial architectures versus some of the commercial architectures and some academic architectures with these, the custom neural processing engines. And then the last part of this plot shows the design using our circuitry. And you notice the energy efficiency is about 200x improvement in energy efficiency, in throughput, and about 400, almost 4 times, as much as 4 times, 400x improvement in energy efficiency. So now we're beginning to see that, yeah, you can achieve 1 to 2 orders of magnitude improvement in both throughput and energy efficiency if you inject these cells into a DRAM architecture. Okay, so now this is one of the most important areas is transformers. So these are your this ChatGPT and other types of neural network architectures. So these are BERT base and BERT large are names of 2 well-known, fairly large transformer architectures. And what we begin to see for these is, for token length of 512, so that's the length of your text, the improvements in energy efficiency over a GPU, right, is now we're about 50x improvement. So now we're in the ballpark of 10 to 100x somewhere. 50x is substantial when you look at the kind of energy efficiency that we need to achieve. So the SIDAN, which stands for computing in DRAM with artificial neurons, you have somewhere anywhere from 8x to 50x improvement in speed up. If you look at designs, this actually extends from 500 token length of 512 to token length of 4096. So this is how much text you can feed this beast, right? 512 is 512 tokens versus 496 tokens. And you see that, again, the improvements both in energy efficiency. This HIMA is a very well-known architecture, custom ASIC architecture for accelerating neural networks. So these improvements that we get in both in energy efficiency and speed up are in the order of at least 1 to 2 orders of magnitude. Okay, my second to last slide. So in summary, what is going on at the moment? We're developing the programming infrastructure. So all of these circuit technologies that people introduce, they never see the light of day for one very important reason. And because there's no software infrastructure, nobody ever provides you the software infrastructure to be able to map C programs or your PyTorch programs or whatever framework you're used to. So we're working on that at the moment. So developing the software infrastructure, which is one of the parts of that is to organize the layout in the memory to meet latency and minimize energy. So if I'm already within 50x improvement in energy efficiency, and if I do my data layouts better, then I should be able to pretty well reach that 100x and probably exceed 100x improvement. We're working on extending a compiler for a PIM extended RISC-V machine. So if we can do this, then we'll have a working processor which has this fancy ALU built into it. Okay. The next part, so these are the known knowns, as we say, are one of my favorite politicians, quoting one of my favorite politicians. Do you know who this is? Rumsfeld, yes. Known knowns. So what do we know? ASIC design. So we've been able to optimize conventional ASIC design, introducing so-called neurons into logic design. Then we took that, and so because of that high compute density, we're able to introduce this artificial neurons into the DRAM. And we showed how this high compute density, high speed, low power, low area, all can be achieved simultaneously. And the nice thing about this is it allows us to have a maximum available parallelism in the DRAM, exploiting the maximum amount of parallelism. So all this sounds great, right? Why am I not rich? Well, then there are known unknowns, as Mr. Rumsfeld used to say. And the known unknowns are those little blue boxes. These are non-CMOS logic, and they're emerging technologies, and nobody has actually been able to design these and demonstrate these at scale and integrate them with CMOS. So there's the Achilles heel of this whole project. Okay? And what that means is these circuits, these devices are, what we're looking at now is ferroelectric FETs, the so-called, what are called hexagonal boron nitride memristors. So this is actually being developed at ASU, and there's ECRAM is being developed at Sandia National Labs, and we may be familiar with this, STT MTJs, these are your MRAM circuits. All of these are devices that provide programmable resistances. Resistances of those little devices that can be changed, right, by program control. That's all we need. But you need to be able to integrate this with CMOS logic. And that's the Achilles heel. If I can get this working, I'll be a very rich man. But I have to get it working before my time ends. So I'm not sure how long that's going to be. Okay? But that's the point. So this is next year, we're trying to collaborate with the group in Technical University of Munich. They have the technology for the ferroelectric FETs that we're going to integrate this circuitry with their technology. And the HBN memristors is being done at ASU. So we're going to follow that path to see if that'll work. And if we can get Global Foundries has these MRAMs. So we're going to work with them to see if we can try MRAMs. And ECRAM is still further out. But this is where the open-endedness of this project is at the moment, to demonstrate all of this in silicon. Okay? And I'm 1 minute over schedule. Thank you for your time.